talk. Let me introduce the speaker. Dr. Shitala Prasad is an assistant professor in computer science at IIT Goa. He obtained his PhD from IIT Roorkee. His research interests are in deep learning, pattern recognition, and computer vision. He is an expert in image analysis and understanding, which is used in industrial applications, biometrics, agricultural or agro-industry, etc. He worked as a scientist at the Institute for Infocomm Research, I2R, at A-Star Singapore before joining IIT Goa. And previously, he was a researcher at NTU Singapore and CNRS France. He's a senior member of IEEE. So we look forward to the talk in this very relevant area. Thank you, Dr. Shitala, for agreeing to give this talk, and welcome.
Thank you very much. Thank you, Neha. So I'll start with my talk. So as per the topic is deep learning challenges in industrial vision. So this image, which you can see, is from Singapore Street, Orchard Road. So the task was something to detect the text instances within the scene so that it can be used for tracking purpose or some kind of activities detection. So I'll start with this. Thanks for the beautiful introduction. Yeah, and yeah, I can go next. Yeah. So I'm IEEE senior member. I'm also a recipient of a NICE fellow in AI in Singapore. Received young researchers in CSI from my IIT Kanpur chapter. Merited awards so and so. I have relevant papers in this content, which includes industries as well as biometrics and biomedical images. Okay, so just to give a glimpse, like what are all I'm interested in. I do work in image processing vision, object detections, and text recognitions. I also work on deep learning and the strategies of trainings, minimized or can be optimized for low-end devices and can be a lightweighted machines. Biomedical and biometrics, of course, is my key interest, along with the data augmentation. Working with 3D object recognitions with multiple views, including continuous learning or kind of like adaptive learning. And also interested in human-computer interactions. Yeah, so coming up to the topic, that is our industrial view. As we know that in industry, we have several hardwares and several uses of computers, and the task is like vision-based mostly. So these tasks are basically need to identify and then do some kind of clubbing and all. So there are basically when we talk about industrial vision, how AI can be used as a part of like vision for human being. So we do have some kind of challenges in industry. That is your data readiness. When we have algorithms deployed already in our lab environment, can it be directly used to industry purpose or not? That's the big question. If it is, then how? Because the data in industries are not so clean. They need some pre-processings, or the data which industry has is very realistic, but which we worked or in lab is synthetic ones or very controlled and are captured in very controlled environment. Then the next challenge which we see is your data annotations, because industrial data are really very tough and challenging. So to annotate them is again time consuming, and in different industries have different applications. So the same algorithm cannot be like modified or cannot be directly used to have on the other applications. So scalability also comes into the picture. So here I will be talking about one of my applications, which is like multi-view learning, where your 3D objects need to be identified. You can imagine with a 3D scenario of an object, which something like this, where you have an object, but that object looks different from different angles. So is it possible for us, human being, to identify them? I think most of the people will say yes, of course, but for machine learning, it's difficult because every single view is a different object for a machine learning, and just to train them to form a single view, object view is a little bit challenging, because there might be some situations where one of your view is resembling to other objects other view. So in that case, we have to have a trade-off. We need to learn those things. Yeah. So here the picturization is based on this picturizations, you can have a clear idea. This is a 3D view of 3D animations of a screw, and here are some of the images where you can see like the same object, first row, the same object has different shapes from different angles. So it's very difficult to correlate them together to form one single objects in a embedding space. So that's how we usually deal. We have so much of challenge when we talk about real scenario. And there might be instances like fan category. And in fan category, there are fans, but those fans are all of different shapes and sizes and different builds, but they all belongs to a same category of fan. So how to make sure that these categories, these objects are close enough to form one single category? That's the challenge in 3D object recognition, 3D multi-view object recognition. So for that to solve it, a very simple approach was adopted in this article. What we did is like we had a big data set, say for example D, which includes all your views from view 1 dot dot to view, say for example 12. 12 because a plane can be divided into 12 views from 0 to 360 degree. If we have 12 images, then can be like 12 views. So that object can be like clearly or completely identified, 100% accurate. So we use that kind of concepts, and we divided this data set into 12 views, and then this data set is further subdivided into D1, D2, so this will be having somewhat like say for example only first two views are used for training a network. We call it as a 3D object classifier. So we train that network with some kind of parameter, and then use loss functions to compute the loss, and then again use the back propagations to update the weights. Based on that, we try to learn these two patterns. But slowly and gradually, we keep on pumping new views to the data sets. In the second phase, we use the same previous weights as an initializer, and then train it on our new views, and then keep on updating the things. Similarly, we add more views and then keep on updating it. So that will actually help us to learn to learn in a better way, because what happens when you give all the views together to the network gets saturated very fast. The gradient or the change will be like almost zero. And then in that case, the network is not going to learn anything beyond a certain point. But if you try to do in such manner, your gradient calculations will be still there alive, and it won't die so fast. So might be chance that your network is learning beyond some certain point, which was not possible in a baseline approach. So that's like a stepwise learning kind of stuff. And other modality which we need to add is like we added a multi-loss function. So this multi-loss functions was a concept taken from a classroom approach, where classroom there is one teacher and teaching several students the same information, but some students are brilliant enough to get that information, some are like average ones. So we choose the best one which has the best or minimum loss functions, and based on that we try to update the weights, and then that's how we try to cut down the learning process. So in that case, it will be like minimizing your training cost, because in that case the conversion will be like much faster. So this is a graph where you can see the learning curve, the accuracy curve for seen classes. Seen classes means the classes which the network has seen before. So out of your why it is not dropping. Out of your 12 views, may be possible that all those 12 views are not seen by the network. So what we did is like while training, we hide 4 views, only train with 8 views, and then see what is the performance on those 8 seen views. And then in that case, we can see like our proposed method is better than the baseline method. This is the baseline method over here. and our proposed method is performing much better than our baseline method. So this is for the seen classes. Similarly, what we analyzed is for unseen classes, those 4 unseen views were now tested without training, and then we saw that at that time also at the time of unseen categories also the network was performing very well compared to the baseline model. The performance differences again still reasonably significant. And we tested this concept with not only one backbone, but several backbones like EfficientNet, ResNet, iResNets, and VGG. And we found that this concept is like inheritable, is heritable to all other models, which is like generally used. That's one approach. And then the next task was like, how can we even further boost it? So we tried to work out with different batch sizes, and then we saw that the performance is also being affected by different batches, batch size of your given data sets. So here the good point is you are not going to increase the number of epochs. The number of epochs is fixed for all the cases for your baseline as well as for your proposed method. Your data set is also fixed for your proposed method and the baseline, but still the performance boost is reasonably significant. That's what we saw in this experiment. Yeah, and because we need to add few layers to the network, we have cut down few layers from the existing network, and because of that, you can see there is a performance difference also. This is the standard baseline method where you had 134 million parameters, but the proposed method has where is it? But the proposed method which we used with a modified version has only 130, and the number of flops is only 1.2, and this one is 16.5. So that's how we can compute for the performance. This is some kind of analytical study where you can see we had some experiment performed on different data sets just to see how the performance is working on different data sets. And then we found that along with seen, unseen categories also like boosting up, and their boost is like improved by 2 to 4%. And the overall proposed learning strategy is like very much generic. But the problem comes with the industrial. The problem with the industrial data is, say for example, mechanical parts. They are like textureless. So in textureless, what extra textures we can have? We can have only the shape informations. So that's a problem for the model to learn. Like if we keep on training it, or if you have a high complicated networks, the network is like not going to train, but might get confused and sometimes get overfitted. So there might be there should be some situations where only the shape features can be adopted. So we come up with a conclusion. What we can do is like instead of just learning the image information, which has a little bit details of your texture information, but along with that we can also have some kind of point clouds inherited, and then club these two embedding space together to form a universals embedding, where your point cloud as well as your image query, normal image query, can be pointed out, and then you can get a results for that. So this way, what we can do is like we can have the benefit of this is you can have only few images of that mechanical part, because we can only we only need the shape information, which is easily addressed by your point cloud that can be like used. So very few shots, very few images can be used for training the network, and the network is good enough to identify them. That part is also like good contributions when you talk about 3D object recognitions, where object shape is important rather than the texture patterns. And the other challenge in this is like when you change the shape, when you change the view angle, the shape has changed. So there will be some what we analyzed is there is some kind of 120-degree angle. If we take images in 120-degree angle, then might be possible that most of the views we can cover for that complete objects, but exact textures won't come. Like in some image, this handle won't come, but most of the time this edge of the cup edge will be coming. So those points can be like memorized or can be like taken as a reference to recognize an object. That part of things we have considered here, and based on that we found like our one shot 5 ways as like outperforming compared to our existing methods, state of the art. So now we were the state of the art method. So this is one of the approach where we can use a few shot learning kind of concepts for industrial object recognitions, where we have limited number of data's accessibilities and a limited number of annotations possible. So we do not have much data, we do not have much manpower to annotate them, but we want to have a solution very quickly. So in that case, these kind of solutions might help. But the situation is not only classifying, but the situation can also move towards the detection part. So in the industry, we need to also detect several objects. These objects might be of same size or might be of similar shape, but size is different. Say, for example, your screw. That screw can be of same shape, but sometimes the screw is smaller. But in computer vision, in deep learning, the problem with the deep learning is it cannot identify or cannot distinguish between two different object size. So that's why we need to have some kind of solutions where this can be tackled out. So we need to have a detector which is good enough to detect. So for now, in this next slides, we will be only covering like text detections, where other than your normal image, other than your foreground images, how background images can be used for handling. Say, for example, this is an example where some meter is being read, and based on that reading, you generate the bill. So that kind of applications you can imagine. But the problem with AI is like they are like highly dependent upon data which we feed in. So they are more or less we can say that they are data centric. So for example, if you want to understand this one more detailedly, so for example, if we have 3 labelers, say for example, labeler 1, labeler 2, and labeler 3, we ask them to label the text instances in the given image. So one labeler has labeled the text instances very precisely, word by word, but one labeler has annotated the text precisely, which is very much visible, but has forgotten this to annotate this one, has also forgotten to annotate this one. So in that case, what happens is like these will be like counted as a noise. So data imbalance. I mean, this will create a kind of data problem. And the other third labeler is even lazier, and he created a one bigger bounding box for complete text instances. So many text instances is represented as a one single text instance. So if you can imagine, like we have a model trained on these 3 data sets, then what can be the output? Here the network is trying to learn or the text instances, but here the network tries to forget that this can be also a text instances. Here the text network is like getting again confused that several text instances can be one single text instance, or there should be like several. So this kind of noise will actually make a network more confused. So I can give you an example of this this article. So if you come into the detail of this one, we instead of just having the object information, we should also have the foreground information. We should also have the surrounding object information. Say for example, here there is a grill, which is basically a road grill. But for a computer network which is trained on text detection, it will detect this grill as a set of n, which is basically a wrong prediction. But because network is only trained on text detection, so it do not know any relations between the other surroundings, like whether this nn is on a roadside or on a sky or on a building number. So for the network, it's a correct one. Similarly, we can have we do have some text instances which is basically a reflection of your actual text instances, and in that case the network actually fails to detect them. So we need to come up with a solution for that. So you can have another view here, where automobiles actually where industries can use this text instances for some purpose. The first image can be used for your tracking a person where the face is not visible, but while he has some text instances on his dress, based on that person can be tracked. Similarly, on the right hand side, you can see a car, there will be a car plate, then there will be a text instances, then you can find the track. and some other images where these texts are having some relations with the objects. So whether it is a medicine name or whether it's just a weight of some objects, something like that. So instead of just having the object information, we should, foreground information, we should also know where that foreground is surrounded with. So for example, if we talk about an example here there is an example. If we just see this image, network has detected this image as an M and with a confidence level of 92%. Here the network has detected this as a 1 or I with a confidence level of 84%. But if you see a complete picture, it's basically a part of a food plate and a woman's scarf. So it's not actually a text instance, but actually network got confused with the text and the real objects. So that's very much possible if the network do not know where that object is lying. Similarly, if you see this one, it's basically for a human being is very easy to make sure that this is an elephant trunk, but for a network, it's the character J. So you can avoid these things by knowing the complete object where that text instance is lied. So that's what approach we have used in this article. We tried to create a positive and a negative attention mechanisms where a network has been taught like, okay, whenever you get some results, you should always check that result is in a positive zone or a negative zone. And based on that, you can decide whether you have detected this should be counted as correct or should be like discarded. So we have created a data set, which we call it as an unconstrained text and object data sets. The same image will have object as well as the text instances, and the text instances are correlated. Say, for example, if you have a person, then person is having some clothes, then person's clothes might have some logo, then that logo might have some text instances. So in case if the detector says that, okay, there is a text instance over here, then the attention mechanism says, okay, this is a positive class. So yeah, this text instance is correct. So in that case, we can avoid the false positiveness or something. So to come up with that solution, we have to have two networks. One network is dedicated to object detections. So there will be some objects which is positive and negative. We'll try to learn that one, and based on that learning, we'll use that weight to be passed to the text detector. Then that text detector will be using that information, the input image, and based on your object detector's attention mechanism, the text detector will be good enough to know that whether the text is at the right location or a negative location. If it is negative location, discard it, count it as a foreground, otherwise count it as a text instance as a background. So that's how it actually learns. There are several phases to learn it because it cannot go in one pass. So we had to have 3 stage of learning. That's like part of process. And yeah, of course, like when we have two different networks together piped in series, we need to have some kind of hourglass approach where this information is not destroyed. So you have to pump the original informations to the next network, so that information is like still maintained and the network is only knowing the positive and negative reason. So this is the block diagram where you can see the positive and negative of an image. And this is some results output where you can see our model is like performing good. And compared to that, we also compared on some kind of visual informations where human eyes usually fails. The text is there, but usually we hard to see it. Some text instances are there, which is very small, but network is good enough to know because it's a signboard. So networks knows that, okay, this is signboard, then maybe there will be a positive class text instances. And some other random images also been taken. And then we try to do some kind of purposefully, we try to introduce positive and negative classes over an image. So you can see like when we introduce a positive class, the confidence gets increased. And when we introduce a negative class, the confidence gets reduced. So that's actually somewhat tries to validate our claim that if we know the background information, of course, the networks gets confident enough to predict whether this object is plus or whether this object is text instance or not, because there might be some characters which is part of a tree, but also can be a part of Chinese characters, because we also learn some we also use Chinese character here, something like that. But the network can be misleaded. So we need to know the background information along with your foreground information, not only the background information. right? So here is some output where you can see the images. On the left side, the detection is happening. On the right side, the reading of the text is happening. So along with this, when we talk about mechanical smart manufacturing, we also need to know that multi-view is not only the thing, but multi-view can be from several ways. So for example, if this is your object, then that multi-view can be at this plane or this plane or this plane or at this plane, something at different planes, if you call it as a plane P1, P2. So what we need to do is like we need to come up with a proper solution where these multi-views can be addressed by a full set of full set of features. So we proposed one methodology where our instance attention mechanisms is being used, because say for example, you have a fan. Sometimes the fan has 2 blades, sometimes the fan has 3 blades. So in that case, the instances are different, but they belong to the same category. So how to map them together? We come up with this proposed solution, and then based on that, this is an output. You can have it, and can have a view. We can have a look. Along with this, we also worked with when I was there in Singapore, I also worked with a COVID task force. So we were asked by the government of Singapore to design some solution within a due time, to come up with a solution where we can monitor a person's with and without mask, and whether he or she is coughing. And coughing, then is it a normal cough, or can we consider as a COVID cough? So those things has been like tackled. So here this problem was simplified to face detection, mask detections with and without. So we tried to learn, because at that time we do not have the data sets. So annotation was also a problem, and that deployment should be so fast that it can actually be used in a real practical way. And also those deployments should be done in a low edge devices. So you need to come up with a solution which is lightweighted. So we come up with a solution where we had a very limited number of data. Say for example, like thousand data sets. So if you are aware of deep learning, this 1,000 image is not enough to train a network, but is good enough to have some kind of initialization, weight initializations. So using that 1,000 images, we created one network and then come up with a predictor, and use that predictor to annotate the unannotated data, and then again use those pseudo annotated data to come up with another predictor, and then keep on using that one, and till we have a satisfactory results. And then after that, we club this pseudo annotated data along with the annotated data, and then come up with a final predictor. And this predictor is then again used for a real deployment. So this was our task, where you can see like we, with a limited number of data, how we can boost up our performance, or we can boost up our deployment phase, where you do not have much data, but you need to have a solution. So this is how we can use. You do not have manpower to annotate the data, because you do not have time to annotate them. So you just start with a very small data, and then keep on using, repeating that data. Use the same predictor to predict more labels, and then based on that labels, you keep on improving your model. And this is the output of that existing predictor. Sorry, the trained predictor, where you can see the yellow box with and with mask, and the red box without the mask. And the problem in this is like we were asked to come up with a solution that wherever the face is, wherever there is a kid without mask, we should not consider that one. So we need to also calculate the age of the face. So if that age is below 5 years or so, we'll discard them. So it's like they don't have to wear the mask, so we can bypass them. So this kind of approach can this solutions was planned to be deployed in some crowded places like airport and other things. This is the video output of the proposed model, and yeah. So at last, if I'm on time. So at last, 35 minutes. So at last, what I can say is like because we are in real world, so everything is non-linear, and therefore their problem is also a non-linear. So whatever solutions we need to propose should be also a kind of non-linear solutions. So you can see like how we need to tackle with different scenarios when we see like different industries. Some industries are working on manufacturing, some industries are working on biomedical, some industries are working on monitoring and controlling. So in that case, whenever we have this kind of challenge, we have to come up with a quick solution. That solutions has to be solved in such a ways where you do not have data, or if you have a data, you do not have time to annotate them. Then how to come up with? So yeah, so most of the solutions, most of the problems are non-linear. So most of the solutions are also non-linear. So that's how we have to. Yeah. So yeah, that's all I have. I think I finished my point. Yeah, 35 minutes. Yeah. So if you have any questions regarding this, I am open to take them.
Thanks for the very interesting talk. I hope there are some nice questions.
Yeah, sure.
Are there any questions from anyone?
You are free to ask questions if you have any, and on any topic is okay for us.
If it's okay, I can get started with. I have one question. So in the Indian context, right? I mean, I'm sure the civic systems are very different in Singapore, but in the Indian context, where do you see the opportunity to apply this technology right away? Like, where can it be? Where is it ripe for application?
Say, for example, if you talk about this last application, the mask one, it can directly be deployed into hospitals and research centers, medical research centers, where you need to have a mask, or some chemical factories where you need to have those things. So you can monitor them using this kind of sensors. That is one application. Next applications, say for example, that 3D view, where you have a car plant and robotic arms are used to design those, or to manufacture the car. So in that case, you have so many screws and nuts and bolts. So and they look like similar, or they have different patterns. So in that case, you can use this kind of approach where few short algorithms can be used. And also, like over time to time, we are upgrading our models. Say for example, car models. So the shape of the parts is also changing. So is it possible for us to every time train the network and then use it? So first of all, when you are going to have a new model, you do not have that many samples. So how to train the network? So is it possible for us to have very few samples and then use it for deployment and then continue our work? So those things can be deployed directly, like in industries where robotics arms are involved or visions are involved, like manufacturing industries. Yeah, two examples I have given. And regarding this text ones, at that time it was being used by Singapore government. So we worked with the CID of Singapore, and we worked with some other task force. So their requirement was something like detecting text, and then based on the text, we can infer or we can track the person. So currently in Indian scenario, I'm not so sure that we do have this kind of smart systems, because Singapore, of course, they had like full-fledged every cameras are working and they are like connected to each other. But here cannot imagine that way. So straightforwardly, that technology cannot be used, but we can plan to have that kind of scenarios in future, where you can use these cameras and these cameras are talking to each other to track someone in a smart scenario. Yeah.
I think
Thanks.
even in automatic ticket generation, right? For example, if you're overspeeding.
Pardon?
If you're overspeeding, if your car is overspeeding.
Yes, that is also
right,
possible. In France, we do have that kind of mechanism. When your car is like overspeed, we do have an IR camera, and then based on that IR camera, they are like automatically generating the billing. So at the time they reach their home, they will get the bill also on the mobile SMS or something. Yeah,
I think they have introduced some sort of it in Goa as well.
Goa also? Oh, I'm not much aware of that.
Where they send this ticket, right? Where they send a ticket with a picture of your car.
Okay.
And the speed that you are on.
Oh, that's
in some areas, not all over Goa.
So maybe there will be there are some challenges to deploy it in mass. So that's why they are just in a trial mode. So if possible, I think that the model
which Nitesh mentioned about speed cameras on Atal Setu.
Okay. Okay, I'm not sure about that.
The new Mandovi Bridge.
Okay, I haven't been that place.
Okay.
Yeah, maybe I'll get to that one once I visit. Yeah, thank you for the knowledge.
There is a question in the chat window from Narayan.
Okay.
It says, how does this model compare with other SOTA models such as YOLOv5 or transformer models?
Okay, so this question is for text detection one. Object detection, yeah, correct. Okay. Okay. So of course YOLO is a bit faster for sure, but the accuracy is compromised when we talk about other models. So here our task was not to have a high state of the art, but also to have not only to have a high state performance, but also to have a lightweighted computing device which can easily be deployed on the existing models, so that, like, say for example, we do have the cameras already deployed in the streets. Then instead of replacing them, we can just plug these algorithms to work along with it. So our task was to have a small and portable lightweighted detector. So that's why we come up with this kind of approach. But of course, YOLOv5 is better to some extent for speed, in terms of speed. And regarding the transformer, of course, transformer is good in performance, but it's very, very slow if you talk about YOLO compared to YOLOv5. Yeah, so that's the answer for that. I think I can see few more questions. So I'm not able to talk about not connecting my power or lightweighted deep learning unless it's time for research helps connected. Okay. Remote sensing and smart. Can you please throw a light on? Okay, yeah. Of course, if you saw my previous model, this model is a kind of like a semi-supervised model where you have very few data, and then based on that, you are training up your network and then coming up with new things. So in this, the problem was, say for example, something to answer your instead of having completely self-supervised, we used semi-supervised. So our model has seen this kind of mask with this kind of strip. But in real scenario, we do not limit with this kind of mask only. We have various masks of different shapes, different sizes, different funny things over here. So networks, our network is like trying to adopt to this kind of mask also over a training period. So for from unlabeled data, it's trying to create a pseudo label with some kind of confidence. Then we are improving that confidence. So in that case, it's good. And if you talk about biomedical field, biomedical, right? Healthcare, biomedical or healthcare, I think self-supervised is still like under research only, because that's like a very serious things. So we still need to wait for a full-fledged self-supervised learning for healthcare department. And smart manufacturing, do we have? Yeah, we do have self-supervised learning. I think I have also an article in self-supervised learning for smart manufacturing. I did not cover here, but okay, yeah, maybe if you want, I can talk to you directly. And the next question is, what about the scope of 3D object detections on vehicles in responding with vehicles information systems? Yeah, infrastructure, of course. Of course, 3D object detections are nowadays coming into a big picture. Now, instead of having 2D informations, we are working with 3D, 4D, even 7D data, that is point cloud and other things, using LiDAR sensors. But again, the thing is, if you want to have a higher precision, then of course you need to depend upon high precision devices like your radar and LiDAR and all. But right now, what I talked about is computer vision. So I mean, vision based things, your RGB images based things, informations are like working very good. So if you want to use 3D point cloud or in something like related to automated driving or self-driving car, so in that case, the LiDAR is coming to the picture. So we need to be like more advanced in that, right? Yet now, I mean, yet we have on the training phase, but let's see how it goes. And next question is, can the 2D screen space coordinates be somehow transformed to 3D real coordinates with just a single. Of course, yeah, there are some works in GAN where your 2D image is like transformed to 3D. We do have some works there, but exactly how that is like used in industry right now is like under some discussion. So application is still a question. Whether it will give us a very precise things, because your 2D information is now converted to 3D real world. So how it is possible? So what we are doing is right now, we are using a GAN based. We are generating a view of third. I mean, we are trying to generate second view, third view based on your 2D information only. So this single image camera will try to create 2D images from different angles, and then accumulate them together to come up with a 3D world object. Yeah, so I think that will that way we can solve this 2D to 3D issue. But of course, if you again come up to a point like what is the procedure level, of course there will be of course a trade-off. Yeah. So is there any other question?
Are there any other questions?
I think there is a comment from Nitish. So I think most of us will be very happy to meet if any of you want to meet for discussions in
Yeah, of
IIT
course.
Goa. Yeah.
Of course, it will be
Yes.
good if we can have a person. I think there is one more question. Let me take it. In previous slide, you have shown some text detections and recognitions. Is this what is it? Is this formed in one step, or is it in first detection and then? Yeah, of course. This one is end to end. This slide, right? This is end to end one. So here we have taken. We do have. I mean, the architecture is something like this. If you remember the previous architecture, they were having a object detector and then the text detector, and then detection bounding boxes or prediction was produced. But in this case, when you are going to read the detected portion, what we do is like we have a text detector, and then we pass that detected portion to a header, which is basically a reader. Then that will be reading. So it's a complete end-to-end process. So while training, we do have to read, we do have to update this reader along with your text detection locations, right? So it's a part of like one complete end-to-end process. So this is a complete network. Of course, there are people who are trying to do in another way, like they detect the text and then they use it for they call some kind of OCR to read that text instances. But that's like in real scenario, it's like not working, because real scenario there are many other objects around you, which is like getting you confused. And OCR, if you talk about OCR, the existing OCRs, they will be failing for these real scenarios. For text, digital, of course, it's working, but for real scenario, handwritten, whether Chinese or whether something, then in that case, this existing OCRs do fail. So the only solution is train it from end to end, train it along with your reader head, and that will be like a complete good solution. That will be giving you a best solution. Yeah. Hope I answer your question.
Yeah, thank you, Dr. Shitala.
Yeah,
On behalf of Goa ACM Professional Chapter, we would like to thank you for extremely interesting talk on deep learning challenges. And we hope to meet you in person sometime and have a discussion. Okay,
sure.
And we hope to have another talk with you soon.
Yeah, sure. Of course, I can have another few topics. Thank you.
Okay, thank you. And I would like to take just 2 minutes of your time to talk about ACM.
Yeah,
So
sure.
this talk is organized as part of our Goa ACM professional chapter activities. We usually hold a talk every month. So as you know, ACM is like the world's largest computing society, and it offers benefits that can advance your career and enrich your knowledge with lifelong learning resources. And we have, okay, so we have ACM members, right? We can have professional members as well as student memberships, and you can sign up for this. Okay, the students and as well as the professional members, and that includes like some of the benefits that ACM provides. Is we have a free subscription to ACM's flagship publication that's called the Communications of the ACM. We have online books, courses, videos, and webinars through the ACM Learning Center. And we have opportunities to participate in local chapters, special interest groups, and conferences all over the world. Okay, and we also have a few optional discounted subscription to the ACM Digital Library. So we plan to have we have a conference in Goa on software engineering research, as SERI for short. This will be held sometime in June. Okay, and also I think we're having an HCP conference that's going to be held high performance computing, HPC, and we hope to have it sometime next month. Okay, so we have a mailing list for Goa ACM chapter that Neha can share.
Okay, sure.
Okay, so I hope to see you all again and with more participation the next time.
Sure.
Thank you again.
Thank you.
And
Thank you,
just
Neha,
a small note, if any of you attendees or also the speaker, Dr. Shitala, if any of you are ACM professional members already, can you just drop a mail to us? We are seeking more members to be part of the ACM Goa professional chapter. So if you're already an ACM member, then it will be great if you can join our chapter as chapter members. So do let us know if you already have the membership. Thanks.
Okay, you can reach out to me on my email address with any of the membership. So you can, I'll just tap it here. Okay, if you are active, if you're already a professional member. Okay, and if you have any information on becoming a professional member or a student chapter member, do let us know. Okay, thank you again so much, Dr. Shitala.
Thank you.